Good morning, everyone. Welcome to Data 8 lecture. So this is our first time doing everything remote. This is Ramesh here. And so again, as I mentioned in the Piazza post last night, this is a big experiment. So if you have any feedback, if things are working for you, if they're not, please feel free to let us know. All right, so today's lecture will be on a bunch of examples. So for the last couple of weeks, we've been learning how to do hypothesis tests and thinking about a framework for conducting tests, right? Going from I have a claim that I want to see whether it's true based on data, formulating a null and alternative hypothesis as the two options, and then identifying here's a way to run the test. That is, we simulate under the null hypothesis and look at the data we got. And so today we're going to do a couple more examples and also cover a few odds and ends about p-values. Today's material is in scope for the exam, but that's mainly because it's review. All right, so announcements before we start. So homework 7 is due tomorrow. The material on the homework will be covered on the exam, so please make sure that you do finish it before. Don't think, oh, just because it's for the exam, you'll use your homework drop. Lecture, office hours, and lab are all online. So again, this is the first online lecture. We have a post on Piazza that has all the details. Feel free to check it out. And then at the end, as I mentioned, there's an anonymous Google form if you have any questions. For lecture, I'll be taking questions from the live Piazza thread. So if you have a question that you want to ask, then please ask it here. And every time I stop and ask for questions, I'll kind of go through and look at the questions there. It's important to keep in mind there is a bit of a delay on the stream. So between the time that I ask for questions and I pause, the pauses may be a little longer than they are in a normal lecture. So just be prepared for that. The midterm is going to be on Friday. As Swapnil mentioned, on Monday, the midterm will be entirely online, so you can think of it as a take-home exam. Please, again, complete it as you would a normal exam. So don't collaborate with others. Do it in a quiet place where you can focus. The exam, we're targeting, it's meant to be 2 hours, so, we're aiming to have it take about 2 hours. And again, you should have received an email with information about logistics. If you have not, please contact our logistics lead GSI, Avery, as soon as possible so that we can make sure that you're set up to view the exam on Gradescope and that your exam will be graded. All right, any logistical questions before we continue? So I'm going to pause for a bit and look on Piazza to see if folks have logistical questions. So please post your questions on the live Piazza thread. So somebody asked the question, is there an online lab today to go over the midterm review? And the answer is yes. So lab will be held online. Again, there are more details on the Piazza post linked here. But there'll be a table in that post that tells you the link that you need to click on to visit your GSI's online section. But before you go and log in, there will be a video walkthrough of the worksheet. So please make sure that you attempt the worksheet, that you try things out, and watch the video walkthrough, and then come ask your GSI if you have questions. Then someone else asks, is there the option to take the midterm proctored in VLSB? And yes, there is. So if you feel like if you don't have a quiet place to be, if your roommate's going to be loud or something, you're welcome to come to VLSB. We'll have proctors there for folks who need. There's a question about can DSP folks go to the proctoring room in VLSB? That is a good question. We will circle back and follow up on the Piazza post. Another question was, is Monday's material covered on the exam? Yes, the exam covers everything up through and including this week. Monday's new material, today's mostly review, but yes, Monday's material is in scope. Someone else asked, is the test longer than previous midterms of the same length? It will be roughly the same length. Obviously midterms vary a little in how long or short they are, but we are aiming it to have a similar length. There's a question about, is the midterm curved, and will the online format affect the curve? There, again, the grading scale in this class tends to be pretty generous. If we write an exam that ends up being too hard, then we'll be more generous with the grading. If we write an exam that ends up being too easy, that's on us, and we'll grade accordingly. There's another question about what if VLSB gets filled up. We'll have a plan or post some information about that. These are good questions, some of which we'll circle back on. All right, looks like that's all the questions I'm seeing for now. So let's go ahead and jump into the material. So for the last couple of weeks, you've been talking about testing hypotheses. And so the way this works is before doing any computation, before thinking about null and alternative, the first and most important thing is to understand in English what viewpoint the question is trying to test. That is, what is the question that you're trying to answer using the hypothesis test? And so for some of the examples you've seen in lecture are, is there some kind of racial bias in jury selection, both in the Swain v. Alabama case and in the Alameda County case? Another question is, are these pea plants, do they have this probability of being purple? So before you even start doing any kind of null alternative, it's really important to understand what the question is asking and what the person doing the analysis is trying to get at. Whether that's a question on an exam, whether that's a question on a homework, or whether that's somebody that you're working with, a scientist, or a question that you're trying to answer in your data analysis. So once you have it, then you're going to formulate a null and alternative hypothesis. And the null is the version of the world that's sort of a chance model. That is, this defines something that you can read it and understand it well enough to know, okay, here's how I'm going to take it and go and simulate. If you go on to take more advanced stats, you'll see the null can also be something where you can do the math from, but for the purposes of data 8, then you want your null to be able to tell you how to simulate and generate a possible version of the data that you got. The alternative is the viewpoint from the question. So it's maybe the null says that the people in the jury are drawn from, or in the jury pool are drawn from the population. The alternative says, no, it's not. There's some kind of bias in the selection. And generally with an alternative hypothesis, you have one of three choices. There's, the choice of just, no, the null is not true, or, the thing we're interested in is more, or the thing we're interested in is less. And we'll see a couple examples that make that a little more concrete. So once you've formulated a null and an alternative, you need some way to quantitatively tell the difference between the two, right? Even in the first part of the class, when we were just kind of eyeballing data, we could tell when, we said, maybe this looks interesting. But what we want is a quantitative way of saying, okay, did the data support the null or did they support the alternative more? And so then we define a test statistic. And a good test statistic will tell you whether the null or alternative is favored by the data. So if you should generally choose a test statistic where going one way leads you towards the null and going the other way leads you towards the alternative. So generally, it should be big values favor the null, small values favor the alternative, or vice versa. So once you set up, you say, okay, here's my null, here's my alternative, here's my test statistic, then you're going to compute the value of the test statistic in the data that you actually got, right? What was the TVD in my data set that I observed? What was the actual proportion or difference in the proportion in the data that I observed? Then you're going to say, okay, this is the test statistic that I got from my data, but how does that compare to what I would have gotten if it had just been chance? And that's where we're going to simulate under the null. So we're going to say, okay, set up a simulation based on the null hypothesis, and then simulate what the test statistic would have been a whole bunch of times. And then, last but not least, compare the results. Say, okay, well, let's look at the distribution of what it would have been under the null, and let's compare that to what I actually got. And if the thing that you actually got seems very unusual or very unlikely, then your data probably favor the alternative. Now, this is nice for a qualitative way of thinking about things, and for some of the examples where it's kind of a slam dunk, then it's pretty clear that you don't really need any way of quantifying that. But sometimes it's like, well, the test statistic that I got is kind of unlikely, but maybe not that unlikely, and that's where p-values come in. So a p-value, which is the observed significance level is the formal name, has a slightly complicated definition, but this is the simplest definition that is still correct, right? We tried to boil down what do we absolutely need in order to understand what a p-value is. It's the probability, the chance, under the null hypothesis. So assume the null is true, then it's the probability that the test statistic is either equal to the value that you got or further towards the alternative. So you say, okay, well, remember before I said, well, you want it to be like small values favor the alternative, big values favor the null. Whichever way you defined it, you need to say, okay, let's look at the probability of getting something like what I actually got in the data or further in the alternative direction. And whether that's like or bigger or smaller, again, depends on your question. And so this essentially in English is saying, what is, like, how likely is it that I actually, if the null is true, how likely is it to get the thing I actually got or something, even more extreme, even more alternative-ish? And so large values of the p-value say, well, if the null is true, then the chance of getting what you got is pretty high. So maybe you should lean towards the null. Whereas if you have a small p-value, then the chance of getting the value you got is pretty low if the null is true, and you should kind of favor the alternative. Okay, so I'm going to stop for questions. Looks like we already have a few questions on the Piazza thread. Feel free to add your questions now. I'm actually going to pause for a couple moments just before I start answering the questions so you have time to type. All right, so we have some great questions so far. So first is, when calculating p-values, how do you know if the sample, if you do whether like sample average is less than or equal to the observed statistic or sample average is greater than or equal to the observed statistic, right? And that kind of gets at this last bullet here, is further in the direction of the alternative. So if you set up, and remember if I go back here, remember I said we have to set up the test statistic to help you choose between the two, right? And so if you set it up so that small values favor the alternative, then your p-value is the probability of being smaller than what you actually got in the data under the null. Whereas if you set it up so that larger values favor the alternative, then the p-value is the probability of being greater than that value. And like what that looks like in code, whether you use like greater than or equal to or less than or equal to, we'll do some examples that make that a little clearer. There's another question about, what is the conclusion when you compare between the simulation and the observed? When do we favor the alternative? So we favor the alternative when this value that you actually got doesn't really match with the distribution under the null, right? So we do the simulation and we get, okay, here's what the distribution would have looked like if the null were true. And we look at the value we actually got and we compare, well, does this look like the null distribution? If it does, then we tend to favor the null. If it doesn't, right? If you have a distribution that's centered somewhere, and then the value you actually got is way, way farther out, then you're going to favor the alternative. Somebody else asks about the difference between p-value and p-value cutoff. That's a great question. We're actually going to talk about that a little later in class today. There's another question about, is there a difference between the p-value being high and the test statistic being high? Yes, right? High values of your test statistic, if I tell you, hey, I did a hypothesis test and I got a test statistic of 7.4, and that's kind of high. Well, that doesn't really tell you much about whether or not my null is true, whether my alternative is true, right? Without context, you can't really know just from the test statistic alone, right? I'd have to tell you, okay, well, I set it up so that like big values favor the null or something, and so on. Whereas with the p-value, if I tell you that, hey, I got a p-value of 0.03, then immediately you know that, hey, that p-value is pretty small, right? We tend to define that arbitrary cutoff at 0.05, and the other cutoff at 0.01. So 0.03 is like pretty small. It says if the null is true, right? If we go back to our definition, if the null is true, there's only a 3% chance of getting the value that we got, or something even more alternative-like. So p-values are nice because they're kind of take away, you don't need to have the context of the question. Next question is, how do you decide if you should use a big or small value that favors the null or alternative? It really depends on the question. We'll do some examples that illustrate that. Someone else asks, what are the different types of test statistic and how do we know which one to calculate? Usually in the examples we'll be working through in this class, it'll be fairly straightforward what the test statistic is, right? The ones you've seen so far have been things like what is the proportion of black jurors or white jurors in the pool? What is the total variation distance, the TVD, between these two distributions? What is the proportion? What is the count? Generally, it's things like this that tend to be fairly simple. The only more complex one is total variation distance, and that's based on if you want to compare two distributions. And we'll do an example of TVD. And one last question is, how do we know what is a good definition of the null hypothesis? And I really like this question, and the answer is a good null hypothesis is one that you can read it and be able to simulate. So let's suppose that you write a null hypothesis for a question and you go and give it to your friend who maybe took data 8 last semester. If your friend can go and read that null hypothesis and say, aha, I know how to write a simulation to do this, then that's a good null hypothesis. All right, so let's do a couple examples. So here's our notebook. Again, if you can't see, if the font is too small, anything like that, I'm actually going to zoom in a little bit. If the notebook is too small or too hard to read, or you can't see the graphs, please make a post on Piazza so I can adjust. Okay, so the first example we're going to do is something called Benford's Law. And the idea with Benford's Law is it says, let's suppose you have a whole bunch of numbers that come from some distribution. And in particular, I guess I don't have a slide on it. In particular, that distribution has values that have many orders of magnitude, that span many orders of magnitude. And what that means is that, you have some data that's like in the thousands, some that's in like the tens of thousands, some that's in the hundreds of thousands, millions. So you have a wide range of possible data represented in your data set, a wide range of possible numbers. And what Benford's law says is if that's true of your data, and you look at the first digit of all the numbers in your data, then you're a lot more likely to see ones, and to a lesser extent twos, than you are to see nines. And so, for example, let's say you go and look at incomes of of people in like a well-to-do neighborhood, right? Where you have, some people making tens, some people making hundreds of thousands, some people making millions, then you're likely to see, if you look at everyone's income, there's going to be a lot more people whose income starts with a 1 than with a 9. So in particular, there's this formula. It's the log of 1 plus 1 over the digit. You don't really need to memorize that. You don't necessarily have to understand how that works. But what it is helpful is to see this bar chart. So this shows us, under Benford's law, we have a 30%-ish chance of seeing a first digit that's a 1, whereas we have less than a 5% chance of seeing a first digit that's a 9. And why is this useful? It's useful because it tells us about what data in the real world looks like. And so Benford's law can actually be used to detect fraud. So, there's an example, unfortunately, I couldn't find the data set, of companies filing for IPOs, or like filing financial statements. And if you look at the financials from companies that file financial statements with the government, then their numbers should follow this rule. And generally, anytime that companies' numbers don't follow it, then that's the possibility for fraud. Same thing with election results. In the 2009 election in Iran, this was used to figure out, hey, let's look at the results from certain counties or certain regions in the country, and folks noticed that the results did not really follow Benford's law, and the places where they didn't were heavily suspected of fraud. And that's not the only place. There've been reports in other places too. So I define this function called first digit. You don't have to understand how it works. Again, it's using stuff from beyond data 8. But I'll show you what it does. So let's say we look at first digit of 1,432 is a 1. The first digit of 733 is a 7, and so on. So I have data on the population of each county from the census. So I have a table with each state. Each county, there's one row for each county. It has the state the county's in, it has the county name, and it has the county's population. So what I want is I want to look at these county populations and see, do they actually follow Benford's law? And intuitively, based on the description I told you earlier, it seems like they should, right? Because there should be some counties that have relatively fewer people. There's like small counties that are not very highly populated. And then there's other counties that are very densely populated, right? You can imagine that Alameda County is probably pretty well populated. So if we look at containing Alameda, then Alameda County, which is where we are now, has 1.5 million people in this data. Whereas, if you look at Otago County, which just happens to be the first in Alabama, it only has 54,000 people. So there's a pretty broad range. And so we should think that the data should follow Benford's law. So what we want is, we want to say, okay, let's take this table and let's add another column that has the first digit so we can compare to Benford's law. So how do we take we have this function that computes the first digit. How do we take that function and use it on a column to get a new column? So hopefully in that pause, you thought that the answer is apply. So we can say counties.apply, and the way apply works, remember, is we give it the function and we give it the name of the function to apply it to, and we get back an array of numbers, right? And we can see that the first 3 numbers look pretty good, right? It starts with a 5, because this is a 5, then a 1, then a 2. So let's add that back on. So we just use with column and say first digit. This. So now we can look at our table and we see that we do have the county that we want. Or the first digit as we want. Okay, so now how do we take this and actually see whether the distribution matches the one that I showed you above from Benford's law? Well, we have to take some way of taking all of the ones and counting up how many of them there are, right? All the twos and counting up how many of them there are. That sounds like a job for group. So if we group by first digit, then this is the results group by digit. And we can see that, hey, there's a lot more ones than nines. And if we actually go and make a table, so we can, this is the counts, but again, to compare to the, distribution I showed you earlier, we need probabilities. So what we want is to go from counts to proportions. So we'll just say, we'll pull out the count column here, and we'll divide by the total. And we can visualize the result by looking at proportion, and we can add the proportions there. And we're adding multiple columns. So we'll also add in the the proportion predicted by Benford's law, which is what I defined earlier as Benford model. So we add in a new column, we save the result, and let's do a histogram of the proportions, right? So if we want to do a histogram of multiple things, then we just give it the column with the labels. Also, since here, the digits aren't really, we aren't treating them as numeric, right? It's not like 7 is 7 times more than 1. These are really different categories, so we should be using a bar chart rather than a histogram. So we'll get rid of the count column, and we'll do a hist based on the first digit. And again, as I just said, we should be using a bar chart, not a histogram. And now we see that the distribution in blue from the data matches up pretty well with the distribution predicted by Benford's law, right? So we can see that, this seems like a pretty good fit, but it's not perfect. There's some, the number 3 seems a little more likely in the data. There aren't as many ones, and ones seem like kind of the biggest prediction from Benford's law that, wow, there's a lot of ones, but it seems like it's a little off. So let's do a hypothesis test to see, do these data match the distribution from Benford's law? That is, are the first digits of all the populations of all the counties, do they actually follow this mathematical model or not? So take a minute and figure out what a good null and alternative hypothesis would be for this question. Feel free to work on your own. Feel free to, message your friends online and chat with them about it. So I'll pause for a moment here. All right, so let's think about what a good null hypothesis would be. So normally this would be the part where I call on folks in class, but unfortunately it's a little hard to do that over the air. So as I mentioned before, a good null is one that you can read and know how to simulate under. And so what might be a good null hypothesis? Well, it could be that the data that what we want is we want to say, well, like the data that we got are just like the chance model specified by Benford's law, right? And so we can write that up. Let's say the populations of the counties of each county is or each county's population's first digit has a probability of specified by Benford's law. Right? So this says, okay, now Benford's law, again, is in this Benford model, Benford's law in the Benford model array. Right? So this says, okay, now let's see, does this fit our test for what we said earlier? Can somebody else who doesn't really know that much about the context read this and understand how to simulate? Well, each county's population's first digit has a probability specified by Benford's law in the Benford model array. Well, I can read this and say, you told me how many counties there are, right? It's just this counties table. And I can say, okay, there's a bunch of them. Their probability comes from Benford's law. Even if I don't know what that is, it tells me, okay, like it's in this array. I can go and read it. And so remember that, chance model doesn't necessarily mean like 50-50 or all the same. You can have different probabilities even under your null. So this is a good null because we can read it and write a simulation based on it. And the alternative is, well, there's some difference from Benford's law, right? So the alternative is the distribution of first digits is different from Benford's law. All right, so now we have a null and we have an alternative, right? The null says that, yeah, the data, in the counties fits this mathematical model pretty well. The alternative says, no, there's not. There's some differences, and I think those differences are meaningful, right? So under the null, well, those differences are just kind of random chance, random variation. So now the test statistic has to tell us, should we lean more towards the null or towards the alternative? And whenever we have a case of comparing two distributions the way we are here, right? If you look at this histogram, we're kind of comparing the blue and the gold at this value, the blue and the gold here, the blue and the gold here. Generally, when we're comparing two distributions for our test statistic, we almost always want to use TVD. Not necessarily, but in this case, because we care about all of the digits and we would just want to see how different is it from the original distribution, then we want to use total variation distance. So the test statistic is total variation distance, but just saying total variation distance, well, it's between what and what. So the test statistic will be the total variation distance between the observed digit distribution from the data and the one from Benford's law from this array. So now take a moment and think about whether bigger or smaller values favor the alternative. So I'll pause for kind of a shorter bit of time here. All right, so normally this would be the part where I ask folks to raise their hand if you think's bigger or smaller, but since we can't do that, I will just talk through it. So Here, if the total variation distance between these two things is really big, then that means that like the blue and the gold don't really match up very well at all, right? And so that means that we should probably favor the alternative because the distributions are different. So here, bigger values of the test statistic favor the alternative. All right, so now we're ready to go ahead and actually do a simulation. So how do we do a simulation? Well, we define what we want to do, assuming the null is true, right? So let's define a function that simulates what the first digits of the counties would be if the null were true. Well, we know we have the number of counties, and we want to simulate that many draws. And the null says, okay, each county's digit comes from Benford's law, right? And this is a fully specified chance model because the Benford's model array tells me, right? I don't have to like write out in my null hypothesis like the probability of 1 is like 0.3, the probability of 2 is 0.175. As long as I can read it and like very obviously understand where to find them, that's good enough. So here, how do we simulate data based on an array of probabilities? We want to use sample proportions, right? So sample proportions, we say we want to sample however many counties there are, and for each one, we're going to use the Benford model as the like probabilities of getting a 1, probability of getting a 2, and so on. And this is going to be the simulated frequencies. And so we can actually just run this outside of our function to make sure it looks good. And yes, this tells us a bunch of probabilities. You know, if in this particular simulated value under the null, you know, 30.01% were 1s, and so on, down to like only 4% were 9s. Great. So now how do we take these simulated frequencies and compare them to the model? Well, we compute the total variation distance. What is the definition of total variation distance? It's we add up all the absolute values of these simulated values minus whatever the distribution says. And remember that we have to divide by 2, right? If we didn't divide by 2, then it would still be a perfectly good test statistic because it still fits the bill of like bigger values favor 1, smaller favor the alternative. We divide by 2 in TVD because, you know, that helps us get a number between 0 and 1, and that's just kind of the definition of it. All right, so then we can return this. And let's make sure that this works. We can run it a bunch of times. Looks like we're getting values around the 0.016 range. And if we compute the on our data, observed, TVD, well, then we can look. If you remember, we defined these arrays up here. So we have proportions. So here, if we do the same calculation and look at the observed TVD, then we can see that the value we actually got is 0.019, which seems to be in the range of the simulations. So again, we need to do the simulation many times. So we'll make an array, and we will, a whole bunch of times, we will take our array and we'll append the result of doing a simulation, right? And again, this by itself is not good enough. This is probably a common mistake that you may have seen on the homework. What we need here is we need to save this back as this, right? And now I'm going to go ahead and take the code to make the histogram from, and now we can see that if the null is true, then these are the possible TVDs that we would get, right? So generally they tend to be in the range of like 0.01 to 0.03, possible to get something 0.03 to 0.04. Remember, this is just how we read histograms, and most of the time it's like just under 0.02. Now we want to compute our p-value, which is again, remember the definition was the probability, if the null is true, that the test statistic is equal to what we got or further towards the alternative. In this question, further towards the alternative means bigger. So what we need is we want to say, okay, what is the probability of getting what we got, which is, observed TVD 0.019, or further towards the alternative, or bigger. So what we want is we want to say, okay, let's look at the simulated TVDs, and let's count how many of them are bigger than the observed TVD. So this gives us an array of trues, falses, trues, and so on. And how do we count how many of those there are? Well, we can use np.count_non_0 and then divide by however many there are, which in this case is 10,000. Or we can also use np.average or np.mean. So in this case, this is our p-value. It's the probability, if the null is true, which is why we're using the simulated values here, of getting something like what we got in the data, or further towards the alternative. And in this case, further towards the alternative means bigger, so we use greater than or equal to. So our p-value is 0.4427. So now, are the data consistent with the null hypothesis? Well, remember that the value we got is like 0.019, right? It's like right here, the p-value is really big in the sense, small p-values are like 0.05. And so what this means is that the value that we got is very smack within the middle of what we'd expect if the null were true. And so then we conclude that the data do in fact favor the null hypothesis. Okay, I'm going to stop for questions. So feel free to add your question on the thread. All right, I have someone asks if I could repeat why I'm using greater than or equal to here as opposed to less than or equal to. And it's because in this particular question, if you remember, if I go back up, remember we filled in this blank here with bigger values of the test statistic favor the alternative, right? And our p-value is always computed like in the direction of the alternative, which means in this case, bigger, right? So there's kind of this like correspondence between how you set up the test statistic and how you compute the p-value. In this case, we set up the test statistic so that bigger values of this test statistic, the TVD, mean that we favor the alternative. And that is why we use a greater than or equal to here. There's another question about, whenever the p-value is less than the p-value cutoff, do we always reject the null in favor of the alternative, or does it depend on whether we decided a bigger or smaller value favors the alternative? So remember that we always compare the p-value to the p-value cutoff, and we say, is it less than the p-value cutoff to determine it? And that doesn't really depend on, whether it's like bigger alternative or smaller favor the alternative. So the p-value is, again, it's just a probability, right? So it doesn't really matter. It doesn't really depend on like what exactly the null is, what exactly the alternative. Interpreting it doesn't require knowing what the null, alternative, and test statistic are, right? Obviously, you need to know all those things to compute it. But if I go and tell you, hey, I did a hypothesis test, and I'm not going to tell you anything about it, but I got a p-value of 0.04, and my p-value cutoff was 0.05, then you can say, you know, even without knowing anything about my test, you know that, hey, that p-value was below the cutoff, right? Which means that that data that I actually got was very unlikely under my null hypothesis. So I should kind of favor my alternative, whatever that may have been. Let's see, we have, why did I not divide the p-value by the number of repetitions? Here I'm using np.average. And remember that average, counts the number of trues and falses and then divides by how many there are. If I were using count non-zero, then I'd have to divide. The two ways are exactly identical. I usually like doing average just because it's less typing. So again, how is, there's a few questions around, is this the formula for the p-value? Is this how we compute it? So let's walk through this one more time. So the way that this works is we say, okay, the p-value in this formal definition is it's the chance if the null is true of blah, 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 blah. So the if the null is true part is we say, okay, let's look at the simulations from the null being true, and let's see how many of them are, in this case, bigger than or equal to the value that I actually got. And so what this says is it's 0.4427, which means there's a 44.27% chance of, if the null is true, of getting something like what I got, or quote unquote more unusual, right? So that's pretty big, right? Like it's like almost 50-50 to get something like this or more extreme. All right, so we are a little short on time, so I'm going to stop, move on from the questions to thinking about p-values and error probabilities, and this kind of gets at a lot of the questions too. So let's think about our tests. Let's take a step back and think about, is it possible to make a mistake, right? Like let's suppose that you're running some tests and you have a null, you have an alternative, and you're trying to decide. Is it possible that your conclusion is wrong? Well, yes, right? I mean, you're not going to be guaranteed to get it right, right? Let's suppose that the null is actually true, right? Let's look at this left column here. Well, your test could favor the null, or your test could favor the alternative, right? It's possible that even if the null is true, that the data that you just got really unlucky, right? Like in this example, maybe like the counties I got that particular year were just like kind of unlucky. Or maybe the jury selection is actually fair. I just got kind of unlucky with the trials I happened to sample. It's definitely possible. On the flip side, if the alternative is true, it could be that the test favors the null, right? It's possible to make that kind of mistake too. And so these two different kind of mistakes have names, and statisticians like to think a lot when doing hypothesis tests about like what are these two mistakes and how likely it is to make each one of them. And so if the alternative is true, then this is kind of, the right column is kind of hard for us to think about because we do all of our hypothesis testing based on the idea that, well, okay, let's assume the null is true and do a simulation and compute a p-value and so on. And so that makes it really hard to kind of reason about what happens if the alternative is true. So let's just focus on the left column for now. And what we can think about is the cutoff for the p-value is actually it's exactly the probability, if the null is true, of making this error. So let's suppose you have a 5% cutoff, right? And the null happens to be true, then there's a 5% chance that your test will favor the alternative, right? If we look at this histogram, these are the possible values I could have gotten if the null were true. And 5% of the time, and my p-value cutoff is 5%, then I'm going to draw the line right here. But 5% of the time, I'm going to be past that line, right? So there's a 5% chance, even if the null is true, that my test will reject the null. And so again, as a reminder, the p-value cutoff doesn't depend on your data, doesn't depend on your simulation, doesn't really depend on your problem setup. You decide on it before seeing the results, right? This is what we say, okay, usually it's like 0.05 or 0.01. And now we know it's the probability of the hypothesis test making an error. The p-value is the thing you actually compute from the data, and then you compare it to your p-value cutoff. And so the p-value cutoff is something you define. It's a number, and we know that it has an interpretation as the probability of making this particular kind of error, right? The error in the bottom left of this table. Error in the top right, that's kind of beyond the scope of data 8. Okay, one last thing for today. So I have another example, or oops, oh, that was here. So one last thing for today. Please fill out this very short anonymous feedback form for today's lecture. It's linked to from the Piazza post. It's linked to from the slides. It's really short. It won't take you more than like a minute. So please go ahead and fill that out. All right, so that is all I have for today. We are right at time. Please feel free to continue posting questions on the Piazza thread, and we'll continue answering them as we go on, and we'll try to think of a way to improve this. Again, as I mentioned, like we're experimenting with this, so if things are working well, if things are not working well, you fill out that feedback form, or you also fill out the anonymous form linked on the other Piazza post. Okay, thank you, everyone.